Hello, Mathemaniacs. I'm the Math Edumacator. This week we're going to be looking at the next major expansion in the number system. Now, looking at this line, you might wonder, where can we put this expansion? We have numbers going this way, and we have numbers going that way. So how can we fit in more numbers anywhere? Before we go into that, let's take a look at what makes this expansion necessary. If I add two counting numbers, I always get another counting number. Makes sense, right? I can always use counting numbers to describe a quantity of individual things, and I can always model addition this way, by putting two groups of things together. If I multiply two counting numbers, I also will always get another counting number. Multiplying with counting numbers is like having a number of groups that are the same size, and then combining them. So it's just like addition in that regard. Both addition and multiplication give us another counting number whenever we operate with counting numbers. These are what we call closed operations, or rather, in this case, operations that are closed over the set of counting numbers. As it turns out, we can actually close operations by expanding the set of numbers that we use. For example, subtraction is not closed on the counting numbers. We can subtract 7 from 4, which is -3, and -3 isn't a counting number. However, if we expand to the integers, now subtraction is closed. Subtraction just involves moving up or down the number line a certain number of spaces. And if we start on an integer and move a number of whole spaces, we always land on another integer. Subtracting one integer from another integer will always give us a third integer. Addition and multiplication will also stay closed on the integers too. So, just like how we expanded the counting numbers to close subtraction, we're now going to expand the integers to close division. Division is the process of splitting a group of things into a number of smaller groups of equal size. Sometimes doing this will give us a counting number. For example, 24 divided by 4 is 24 things split into 4 groups. Each group has 6 things in it, hence 24 divided by 4 is 6. However, suppose we have 25 divided by 4. Well, 24 of those 25 can be split evenly into these 4 groups. But now we have this one left over. This leftover candy is called a remainder. If I put it in any of the 4 groups, they won't all have the same size anymore. The only way I could make the groups even would be to cut the remainder itself into equal parts. So if we did that, each group would have 6 and a little. It's more than 6 whole pieces, but less than 7 whole pieces. And thus we have our answer. This expansion fits in between the integers, in these spaces right here. And we call these numbers the rational numbers. So let's take a look at what these rational numbers look like. I have a pi here. Now I want to take this quantity and split it into 4 even groups, which would be a way of representing 1 divided by 4. Now the best way to do this is just cut the pie into 4 pieces, like so. Each piece is the same size, and there are 4 of them. So now we have our 4 groups. How do we quantify the amount that we have in each group? Well, if we look at these pie pieces, we might see that it looks familiar, like something we learned about in elementary school. It's actually a fraction, specifically 1/4. For those of you who like a refresher, a fraction is when you split something up into multiple equal-sized pieces, and then you have some of those pieces. Every fraction is defined using 2 numbers, the numerator and the denominator. The numerator tells us how many pieces we have, and the denominator tells us how many pieces we need to make one whole thing. So that's like telling us how big the pieces are. So this portion here would be 3/4, or 3/4, because there are 3 pieces, and I would need 4 pieces to make a whole pie. And this portion is 1/4, 1/4, because I have 1 piece, and I would need 4 pieces this size to make a whole pie. Now, interestingly enough, 1 and 4 are the same numbers I used to model my problem, 1 divided by 4. This suggests a link between fractions and division. Let's try another one. Now we're going to model 2 divided by 3. So I've got 2 brownies. I need to split them into 3 groups. The best way to do that would be to cut each brownie into 3 parts and then start putting the parts in groups. So now I have 3 groups with 2 pieces each. Now each group is a fraction again, but what fraction is it? Well, this group has 2 pieces. If I had 3 pieces, that would be a whole brownie. So this is 2/3. 2 over 3 is what you get when you have 2 divided by 3. It turns out this is true of any division problem, which is why we tend to write division in fraction form like this, particularly once we get to algebra. The top number is the dividend, the bottom number is the divisor. So dividend divided by divisor, top divided by bottom. So our new expansion, the rational numbers, contain all of the fractions, but they also include things like -1/2, so the opposites of fractions. The formal definition of a rational number is a ratio, hence rational, where the numerator and the denominator are both integers, and the denominator is not 0, because that would be division by 0. Now, by this definition, the rational numbers also include the integers, just like how the integers included the natural numbers. Every integer, such as 4, can be written as that integer over 1. So in this case, we would have 4 things, and each of those things is 1 whole. Now let's look at these two rational numbers, 4 over 1 and 1 over 4. These numbers are exactly the same, except that the top and the bottom are flipped around. Numbers like these are called reciprocals. The reciprocal of any integer is just 1 over that same integer. And in reverse, the reciprocal of 1 over any number is just that number. For any other fraction, to find the reciprocal, all you have to do is flip from top to bottom. Now, what are some properties that reciprocals have? Well, let's see what would happen if we multiplied these two numbers together. This pie piece, 1/4, we're going to multiply it by 4. So we need 4 pieces this size. So that gives us these 4 pieces, and those 4 pieces make a whole, which is 1. So adding a number with its opposite will always give you 0, and multiplying a number with its reciprocal will always give you 1. So that makes it like division, right? Because it undoes multiplication. Indeed so. Any division problem, you can rewrite it so that it involves multiplying by the reciprocal of the divisor. So if I had 2 divided by 3, that would be the same as 2 times 1/3, or 1/3 of 2. So we cut 2 into 3 pieces, like we did before. However, what if we had 2 divided by 1/3? That seems a bit hard to interpret, but if we remember our reciprocal rule, we can be like, oh, that means 2 times the reciprocal of 1/3, which is 3. And 2 times 3 is 6. That's it for today's video. The next 2 weeks will be more in-depth strategies and rules for operating with integers, and then for operating with rational numbers. So stay tuned. Thank you for watching. If you enjoyed this week's video, please like, comment below, and share the link. If you want to see more, subscribe to our official YouTube channel and follow us on Twitter at Edumacator.